architecture, and I think you know some memory parts of the computer. But anyway, I just want to give you some fundamentals of the memory. So we'll sketch the general organization of computer, including central processing unit, control bus, address bus, data bus, RAM, ROM, and VRAM, and bulk storage memory devices. So given small semiconductor memory organization, we'll draw the memory in table form as a truth table, sketch a logic symbol for the memory, and explains the programming of the memory. But some part you need to read in the chapter. It is chapter 11. We will detail the inputs and predict inputs and outputs and predict operation of small static RAM. So we'll consider some integrated circuit and analyze the input outputs and summarize the operation of larger static RAM. So you can find in the book chapter 11. So we'll program a small static RAM with the gray code. It is actually in the, you can do it on the LabWorks. Characterize read-only memories, analyze a primitive diode-ROM circuit, and solve a counting problem using read-only memory. So I will give some example. So actually, but we could not do it because in the multi-slim we don't have actually ROM. We have RAM. We have ROM, but it's not. We could not simulate this ROM. Okay, so what is the most important characteristic that a digital system has over an analog system? Do you know? One of the most important characteristic. It's actually the ability to store data for short and long periods. So with analog, it's practically impossible. If it's possible, it's very difficult. But with the digital system, we can store data for short. For example, we considered latch, if you remember, and also we can store in the long periods. For example, in some flash cards or maybe in CD or DVDs. So actually, the information revolution occurred due to the availability and use of memory in digital storage device. For example, internet itself is just, we transfer from one, server to other to the user some information. So just even the development of internet, it's based on the memory revolution. So actually, I've said this, and but another interesting device is memory device, a USB flash drive, right? So especially in the near past, it was very popular. So it's actually this USB flash drive is one of the advanced in the memory technology. But of course, now you see that people now use USB flash drive, but not so often, right? I mean, these small portable ones. We prefer to save our data in some clouds in the internet. But anyway, this development of this USB flash drive was very step in developing in computers. Okay, so actually, what types of memory you know in a computer? What kind of memory you know?
Random access memory.
ROM.
Yes, right. So actually, we can roughly divide on two parts, right? First, it's some internal semiconductor memory devices, and second part we can say some external memory devices. So we can say bulk storage device. So if you talk about the internal semiconductor memory device, yes, if it's some RAM, random access memory, some ROM, read-only memory, but also there is actually the same. NVRAM and RAM, the principle of working the same, but NV, it's not volatile RAM. So actually it can store the information even your power is switched off. So when you switched off the power of the integrated circuit of the RAM, you will just lose your information. So in the ROM, information is just exists permanently, right? Here in the RAM is temporarily only during the working. NVRAM actually can save information. Okay, but about external memory devices, it's some hard disk drive, right? It's now very popular CCD, the solid state drive, USB flash memory devices, some, I think CD and DVD is already old-fashioned, but anyway, still we're using this. Okay, so what's the heart of any computer?
Process.
Yes, it's central processing unit. For example, let's consider this figure. You can actually find this in the book, chapter 11. So some primitive, how data transfer occurs in the computer. So actually it is a central processing unit. We can say just processor, right? And you can see a lot of data transferring, storage occurring. So here you can see RAM, ROM, and VRAM, and this it is some kind of bulk external storage. So if you take attention, here we have some, for example, control bus, address bus, and data bus, and now we'll talk about this in more detail. So, but if you take, okay, let me show maybe in the, so if we're talking about central processing unit, so actually it's do some operation, for example, arithmetic, logic, some maybe control, but it need to send information, maybe save somewhere. So all of this memory is available for processor. For example, I said that here you can see, right? For example, three type of bus. So the address bus and the control bus lines. So what is a bus? So bus is a group of parallel conductors whose job is to transfer information to other parts of the computer or microprocessor. So actually the address bus and control bus is what, pay attention, are one-way communication lines that tell memory, storage, and other peripheral devices what does, who does, and what and when. So actually this one-way transportation of information. But also here you can see the database bus, and you can see here arrow, right? It can go to the CPU and also from the processor to the processor. So the data bus is two-way communication channel for sending information to and receiving information from memory, storage, and other peripheral devices. So it can be sent to monitor, for example, or you can send from the keypad. Okay, here what you need, I will mention, so please notice about that. If you look carefully, it is not, of course, in color, but anyway, you can see that here you can see on RAM we have, can you see? Notice that data from the database can flow into, actually can write in memory or out of read from memory, both random access memory RAM and non-volatile RAM. So here you can see that we can, data can come to the RAM and we can take it from the RAM, but here you can see arrow, so it can we can give information and take information. So actually we can write information in the RAM, but on the ROM we can only take, right? We could not write on the ROM because it's just, you know, I will show you some integrated circuit. Actually, manufacturers already they produce this ROM and the data already inside, so we can only read. But on the RAM we can write and further process. Okay, so let's talk about a little bit about semiconductor storage cells because now they're more popular. I will not talk about the, for example, CD, DVD, or maybe hard disk, because I think in the future we will have only semiconductor-based storage cells. So actually we can classify semiconductor storage device in six categories. So let's consider each of them separately. So first is static random access memory, right? So what's the features of this static random access memory? High access speed, read or write, so you can read and write, requires continuous power. So it's volatile memory. So volatile, in Russian it will be испаряться, it's volatile memory. You can only store information during the processing when your integrated circuit is powered on. When you switch off, you will lose your or data. So next, dynamic random access memory. I think they both they do the same thing, but the technology is different. So if the technology, for example, here we use some other kind of transistors. Is different, but they do actually the same. Of course, this dynamic RAM is better than the static RAM. So in most computers, I think we use more this dynamic random access memory. So also this good access speed, read or write, volatile memory, plus a need for refresh circuitry. Yes, what difference? Here we do not need any refresh circuitry, but here we need some refresh circuitry. But do not think about this. It's just for general information. Okay, so this type of RAM we use in most modern personal computers. So next, it's read-only memory. So you can see it's high density, non-volatile, cannot be altered, so reliable, low cost, especially at high volumes. So if you order in high volumes, it will cost not so high. So next, for example, it's also ROM, but it's electrically programmable read-only memory. So actually, you can program it, but it's not easy. You need special device, burner. So actually, you can change the code inside this ROM. So next one, it's EEPROM, electrically erasable programmable read-only memory. So not volatile, but electrically erasable by bytes for reprogramming, lower density, high cost. Okay, next it's flash memory, so very high density, low power, not volatile, but rewritable. So what difference? We can rewrite bit by bit, if it's here by bytes, right? So guys, I think you can read all of this on the book chapter. Maybe you already know and you will study computer architecture. So you will study, or maybe you already studied in detail this one. Yes. Do you have? Did you have the computer architecture course?
Yes.
It's not clear. What you said?
Yes.
Okay. So there is other type of RAM. For example, its technology just different. It's a ferroelectric RAM. It is magnetic resistive RAM. So now this RAM, I think it's one of the best. It is a future. With time, I think it will replace all of this because first of all, it's high density and all this due to the speed and other. It's more preferable, this one, magnetic resistive RAM. Okay, here's some chart. So if you look, you can see that here at the center we have flash and so magnetic resistive RAM. You can see that they have the better combination of these features. High density, it means just how to say the high density. Do you understand what they mean? High density. It means amount of information that it can store. Not volatile and electrically updatable. So you can see that flash and magnetic resistive RAM has better combination of all of these properties and features. Okay, so sometimes RAM is also called scratch pad memory. So now you understand why people sometimes say it's scratch pad memory. So the RAM is a memory that you can teach, right? So after the teaching learning process called writing, the RAM remembers the information for a while and the RAM stored information can be recalled or remembered at any time, but only during the time when the power on. When power off, you lost all information. So, okay, since this, yes, for example, if you look, for example, let's consider some calculators. I don't know, think about this as some real calculators. And so I want to do some, I don't know, multiplication, for example, 9 So now I store 9, right? So it is in RAM, this 9, I'm storing this in RAM. So for example, divide by 3, it will be 3. So all of this will be on my RAM. So if I switch off, then I will open it again, you know that it's not stored. So let's consider this interesting table. So actually, you write the data, the information. You know, you can imagine like you write like in this table. So here you can see address. So we need address, and also we need some we need some cells where we can write every bit. So you can see that we say that these 4 bits, we say just word. So you can see the address of the first word is 0. So you can write down here zeros or 1. So it is a second word. You can see its address is 1, 2, and up to 15. But of course, it is in decimal. So actually, when you write, you need to write in the binary. So actually, address of this first word will be 0000. Of this 0001. So in this example, you can see that. So this is semiconductor memory with 64 cells in which to place zeros and ones. So it's illustrated here in this table. So actually, this, if you count, so actually these 64 bits are organized into 16 groups. So we call these groups, we call these words. So each of these 16 words contains 4 bits information. This memory is said to be organized as 16 of 4 memory. So it means 16 is words, and 4, it means every word has 4 bits. So that contains 16 words, and each word is 4 bits long. Okay, but it can be organized other way. For example, this 64-bit memory could be organized, for example, as 32 words, but in this case, we'll have only, for each word, we'll have only 2 bits, right? For example, you can organize like 64, and in this case, for each word, you will have only 1 bit, or you can organize as 8. So it means you will have only 8 words, and each word will contain 8 bit. Some integrated circuit that actually is some static RAM. So of course it's old-fashioned. It's not already. Nobody uses this, but for the educational purposes, you can still find and buy this one. So it's a very simple one, but it's so old that even in the Multislim, I could not find this one. So it is a 7489 read-write TTL based RAM. So you can see it's 64-bit data storage unit in the integrated circuit form, right? So let's consider its how to say, yes, logics. You can say it's logic symbol, right? So you can see that how much input we have. Here we have 4 input. Here it is a data input that we want to store inside of these RAMs. Also we have address, so where we want to store our data. And also we have some control input. So actually it's control bus, so it is a data bus, and it is the address bus, so what we'll talk about at the beginning. So to understand how to write and how to read from this RAM, we need to consider, of course, kind of truth table. So guys, you need to pay attention to this bubble. So here you can see you activate memory enable, you activate by law, and write enable, you activate also by law. So let's consider, for example, if you want to write some information in this RAM, you need to apply to the memory enable and write enable, you need to apply law. So when you apply memory enable, it means that you can work with this memory. You can write from this memory, you can write to this memory, or you can read from this memory. So write enable, of course, is understandable. So when you activate, when you apply 0, you can write information. So in this case, you apply here some data. I don't know, maybe 1 0 1 0, and next you need to specify in what word you want to save this data. So you give the address, and in this address, this data will be recorded when memory enable and write enable will be low. So next, let's consider. But for example, you don't need to write. You already read some information. You want to read. So in this case, you need to apply to the write enable. You need to apply high. So in this case, you give some address. So when you apply here high, it means this data inputs will not be transferred. So it doesn't matter what will be here. So you disable to write, and you just give the address inputs, and you will get outputs. So for example, if you get for example, you give address 0 0 1 0, then on the output will be the data that you stored in this address. Also, some inhibit storage, you can see high low. So if you apply to the memory enable, you will apply a high, and the write enable low, complement of data inputs. So what will be here will be on the output, but of course it will be, you can see here bubble. So it's actually not actual data, it's inverted data. So to get true data, you need to connect to the inverters. Okay, so let's consider a last one, do nothing. So when you apply high, all outputs high. So it means that here we have 1 1 1 1. Okay, unfortunately, I could not find this on Multislim. And actually, I find on Multislim only one RAM. So let me show you this RAM. Okay, this I will show later. So guys, actually can also test. So I find this RAM 2K8 RAM. So can you see how much data input I have, how much address inputs I have, and how much output I have?
10 input.
8 inputs. We have 8 data inputs, right? From the 0 to 7. So actually it can store 1 byte, right? Next, how much data address? So you can see 12. And outputs, you can see we have also 8 outputs. So guys, if you look carefully on the connection, I just want to use this like this, you know, as this 64-bit, because it's this not 64-bit. So I just want to use that 64-bit. For this reason, I just connected. So I just using D0, D1, D2, D3, and D4, D5, D6, D7. I just connected to the ground. They always will be 0 0 if I will write in the memory. So next, if I will use this only for input, I do not need so much data address input. So you can see I connected all of the from the A4 up to A11. I also connected to the ground, because to store 4-bit information in any combination, you need only how much? You need only, yes, it's enough to 4 address inputs. Okay, so let's test, but also you should see the difference. So if here you can see the bubble, but here you do not see any bubble. So it means you activate this this write enable the same as this write enable. This CS, it means chip select. It's the same as the memory enable. So just different manufacturers, they just, you know, change a little bit their this labeling, but the meaning is the same. But what really is different, you activate by high, not by low. Here you activate by low, but here you activate by high. So let's check this one. So first, okay, now my date put now undefined because we just started and there is no any information here inside. So let's write something. To write, guys, you see that we need to give low, yes, but in this case we activate by high. For this reason, what's moving? I could not understand. For this reason, I just give. So let me also.
So teacher, when we are reading some information, we need to put to hide, yes? Right enable and the
Chip select, yes, you need to put high. Yes, high. So because we don't have this bubble, actually you can connect here inverter, and you can use you can actually use this truth table if you add here two inverters. Okay. So guys, let me restart this one. So it's some simple RAM. Why it's moving?
But anyway, will you open the attendance?
Okay, so let me open the attendance, yes.
Mm-hmm.
So where's our attendance, digital system, attendance. So this lecture, right? Today's day, okay, so I will open. Okay, guys, try to record your attendance and let's continue. So I just want to show you how to write. So I've started, guys, and I need to put chip select and write enable to the low or to the high. So do not confuse with this one. So because here we activate by low. So now I want to record, for example, I don't know, let's record 8. It's my address input. So I want to record, for example, let's choose some address. For example, I want to record on the word 3. On the word 3, I want to record, for example, how much? It is 8. Okay, so next, what I need to do? Next, I need to write enable. I need to switch off. So guys, and let's I will change the address. You can see now I'm referring to the to the 0000. I'm referring to the first word, right? But I recorded in decimal 8. I recorded to the address 3. So let's read this information. So you can see. Can you see? So now I'm giving input 001, 0011, and you can see my data input now 0000, but on the output I have 100. Do you see? Is it clear? Because I've recorded this data I recorded on the word 3. So let's So let's record, I don't know, in what word? So maybe in the word 4. In the word 4, I want to record, for example, 10. So I'm recording 10 in decimal, 1010. I'm recording on the word 4, right? And next I'm just disable writing. So let's come back to my 3. So I'm referring to the word 3, and you can see it's 8. Now I will refer to my word 4. So you can see 1010. So like this, by the switch, step by step, actually I can store data. So how much data I can store? So in the bit I can store for 64, right? In this combination, and in the word I can store only 16 words. So do you have any question for this round?
Yes. Teacher, can we rewrite data from address?
Can you repeat the question? Can you write what?
Can we rewrite the data from same
Yes.
address?
Yes, of course, let's do it. So do you remember that we recorded, for example, on the 4, address 4, we recorded what? We recorded 10, right? So let's record, I don't know, let's record 15. And so now let's check. I disable. And let's come back to the initial. And we're referring to the 4, and before it was 1010, now it's 1111. Okay, of course we can rewrite, because if we will not rewrite, for example, now we're working with your computers, and all of the, many data we store temporarily in our RAM. For example, it's not needed to store a lot of information. For example, when you copy something, copy paste, copy and paste somewhere, so it's all kind of stored in the RAM. So of course we need to record again on the same address when we want to. Okay, so I think if it's clear, so let's move further. So it's all to one, so just for the explanation. But there is other kind of static RAM, but it is based on the previous was TTL, it is MOS. Metal oxide semiconductor RAM. This technology is different, so you can see this 2114. It's also old ones, and also you could not find in the multi-slim. But what here? Can you see difference? Who can say difference between this one and previous one?
There's no data to input.
We have more address inputs.
First of all, yes, we have more address inputs, but you could not see the data inputs. Actually, we have these pins. They perform double function. So you can. So if write enable is active, it means that these pins you use as data input. When you when you deactivate write enable, so this pins will be your output. Do you understand this?
Yes.
So just to save, why do we need to use a lot of pins when we just use these 4 pins as a data inputs or data outputs. Okay, so important characteristic of a RAM is the access time. So we need to understand. So the access time is the time it takes to locate an output or input a piece of data. So for example, we just considered 74890 TLRAM, so its access time about 33 nanoseconds. So when you give some address, so during this short time, it will give you your output. Okay, so but this one, you can see on the most technologies, you can see its access time 250 nanoseconds. So it take longer time to access your data. So of course, in computers, it's very important to have short access time. Okay, so let's consider, guys, I'm just giving some basics, read-only memory. Okay, so many digital devices, including microcomputers, must store some information permanently. So it's really different from the RAM, because RAM, we store information when we're doing something, you know, in some real time. But of course, we need some other kind of memory that will store information permanently. And for this, we need to use read-only memory or ROM. Yes, the ROM is programmed by manufacturer to the user specification. So of course, inside your mobile phone or computers or laptop, of course there is a ROM, and there is some code. We do not say software when we write something on ROM. When it performs some kind of function as a software, we don't say software, we say firmware. I think you know it. So actually, but you know, it is not. For example, if you find somewhere some ROM, for you it will be, you know, you could not use it because this ROM will do some special task. So you could not do other tasks with this ROM because it's permanently already written some code, and if you will power this ROM and will connect to some circuit, it will perform the functions that already permanently were written by the manufacturer. Yes, but if you need some ROMs, for example, for your some circuits that you design, actually you can create this read-only memory yourself by using this combinational logics problems that I've taught you in our previous lecture. So today I show you some simple primitive examples, but you will understand this principle. Okay, so ROMs are classified as non-volatile memories, right? Not volatile, it means не испаряющий, то есть не исчезает, because they do not lose their data when power is turned off. So the read-only memory is also referred to as a mask-programmed ROM. The ROM is used in only high-volume production application because of the expensive initial setup cost. Okay, but there is some reprogrammable read-only memories. So if you do some project maybe in the future and will, for example, I don't know, create some microcomputers that will perform some task, maybe you need some ROM. Of course, you do not need to buy a ROM because it will be very, very expensive. Manufacturer will, you know, I don't know, maybe they produce at least 100,000, you know, but you do not need so much. So you can just buy some programmable read-only memories. Then you can actually program your code inside, but it's not so easy. It's not as with flash memory. You need some burners, so it's not so easy. But anyway, you can do it. So guys, I want to show you some example. And do you remember the gray code? So okay, let's remind you the important characteristic of the gray code is that only one bit changes as you count from top to bottom, as shown in table. So look, guys, this is a decimal and it's a binary, right? And let's compare binary and gray code. So for the decimal 0, gray code will be also 0, 0, 0. 1 will be the same, but 2, you can see it's different because we change only one bit. We do not need here. For for example, you change 2 bits, so you change this least significant to the 0, next you to 1, but here you just change 1 bit. So you can continue. So it is a gray code. And it's quite difficult, yes, to translate from decimal number to the gray code in your mind and back to the decimal again, because it's not so, you know, straightforward for us. But there is a method for making this conversation. So, but we usually use electronic decoders to do the job. Actually, electronic decoders that we studied for decode BCD to the 7-segment display, for example, or decoders that decode from the BCD to the decimal or from the binary, all of this actually it is a ROM. It is a ROM. And now I will show you some primitive Dayat ROM programmed with gray code. So actually this, it's some simple primitive ROM. So it can convert from the decimal to the gray code. For example, it's some switch. If your switch on the 0, the output will be 0, 0, 0. If, for example, in this case, it is on the 6, so you can find from this table that 6 in gray code will be 1, 0, 1. So you can see that C and A will light. It means that it is 6 in gray code. Okay, so the trick that you need to connect Dayat, and actually it's connected like once in this table. So look, so here first, this Dayat is connected only to the first less significant bit. So next 2, it's 0, 0, 1. So this 2 Dayat is connected. Okay, so let me show you this on the Multislam. It's very interesting to assemble this primitive integrated circuit. It is this primitive ROM, and I'll show you my version. So guys, here I introduced new type of switch. It's very convenient to use. So actually, for example, if I press, oops, something happened. What happened? So let's try. Let me try again. So I've checked. Actually, it's worked. I don't know what's happened. It's working. For example, guys. In my keyboard, keypad. So it means that this switch, can you see here? Maybe I need to increase. Can you see? Can you see this movement of this bar here?
Yes.
Or not? Yes. Okay, fine. So, for example, I press 1, and you can see that 0, 0, 0, 1. So it's according to this table, gray code. So now let me press 2. So let's check. Yes, 0, 0, 1, 1. So let's check other. For example, 8, it will be 1, 1, 0, 0. So 8. So 1, 1, 0, 0. So tomorrow on LabWorks, we need to assemble this kind of primitive circuit. Actually, it is a ROM. So the purpose of this ROM is just, you know, convert decimal input to gray code. That's it. So you could not use this one for other purposes. So you could not convert, reprogrammed it to, for example, to convert from the decimal to binary, because for this you need to just reassemble your Dayats, but it will be very difficult. Of course, it's easy in the Multislam, but in the real hardware version, you know, I think it would be silly to do this kind of job. Okay, so I guess
Sure.
yes.
Why do you need gray code?
why we need gray code? Actually, I explained. So gray code is very good. You know, when, for example, if you will work in doing some embedded systems, and you know, for example, you want to do some car that will move, and you need to, for example, find the position of the wheel with time. So you need to code something. So gray code is very good to, you know, to code the position or rotation of your wheel. So it's better. It can be performed by using gray code. So actually, I think I explained in some of the slides. So maybe let me explain in Russian. So gray code очень популярен для тех, кто занимается, скажем, робототехникой в этих вот. Они, допустим, его используют, чтобы находить положение. Скажем, у вас есть моторчик, на моторчике у вас, скажем, есть какая-то стрелка, да, которая вращается. Чтобы положение этой стрелки находить, грей код очень удобен. Ну, в каком-то слайде вроде я даже показывал, как это делается. Shaft encoder. It's called shaft encoder. Okay, so I think, guys, now we can take break and then we'll continue. So yes, relax, take a break. Do you have some question you can ask during this, you know, break time?
How can we increase our average grade?
Guys, you can increase your average grade just by, you know, submitting more lab work. So I give you opportunity. So it will not be any test anymore. So test is over. So I graded you for the test. What test? 4, 6, not 6, 6, right? 7, 8. Or no. I graded you for the 4,
5, 7, 6.
Okay, so 3 tests will be, I graded you for the 3 tests in this end term. So you could not change this grade. Next, I graded you also for the labs. So, and I already uploaded on the Moodle, I uploaded lab 11 and lab 12. So if you want to improve, please do this work and I can, you know, you can get additional several grades and it will improve your average point. Do you have any questions?
Can we show you lab 8 and 9 tomorrow?
From the 8 to what?
9. 8, 9 lab work.
No, guys, now yeah, you need to show me during the lab works, and tomorrow from the 2 p.m. up to 5 p.m. I will be available. So you can show me tomorrow during the lab works and afternoon from the 2 to 3.
I have only
To 5.
2 grades, teacher. For test 4 and 7.
But you showed me other labs?
No, not test, I mean. Test. 4 and
Test
7.
4 and 7?
You didn't
What?
grade test 8.
Okay, tomorrow can you send me on the lab work and then I will grade you, okay? У кого каких-то оценок не хватает, завтра в течение лабворка подходите, им говорите, им я проверю и буду ставить эти оценки. Хорошо? So actually, tomorrow is the last day, last opportunity to affect your midterm grade. Then will be final exam, but before the final exam, I will create some meeting and will add for you all, and we'll talk about the exam in more detail. Okay, guys, in this case, I will take a little bit break and see you in 15 minutes.
Okay. Should we stay in this meeting, teacher?
Yes, I created for 2 hours, so we'll be here. Okay, I think we can continue. And have a few slides to share with you. And so I just showed you this example. How can you assemble some simple ROM that will just, when you power on, you can convert from the decimal to the gray code. So, but here it has some disadvantages. First, because we're using the diodes, the logic levels are marginal. So actually, it's very important for the output will be in some range. So for the diodes, can be too low. So it's just maybe between 2 and 3. It's not so good. The diode ROM also suffers in that it has very limited drive capability. Yes, it can be true. So it could not provide enough current. Okay, so guys, let's consider this one. It's actually similar to the previous one, but here we converted from the decimal to gray code, but here your input is the binary, right? So then this converter will not convert it, the decoder. This decoder will convert to the decimal, and decimal input is connected to the proper connection of these diodes, and your input will be binary. Then we have some medium state when this binary will be converted to the decimal, and from the decimal it will be to the gray code. But of course, you can skip this part and come up with some logic circuit that will convert from the binary, directly to the gray code. So of course there is some practical ROMs are available from many manufacturers, but I said that they already has some code inside. So for example, there is some TTL 74S370. So you can see it's how much bit, 2048 bit ROM organized as a 5012 word. So it has 5012 line, right? And in this line you can organize 4-bit information. So what else? For example, some CMOS based here. So you can see 524,288 bit ROM. So it's organized as 65,536 word by 8-bit memory. But of course, in the computer ROM, actually, it has a larger capacity. Okay, this is the scheme of this read-only memory. So what you can see is here. So it has how much? 13, right? Address inputs. So here we have inputs, outputs, data. We have 8 outputs, and of course VCC and ground. But also there is E, or E is the same. So E NOT, it means you activate by. It depends. You can actually custom this. If you will order, you can custom. So you can activate by low. It means it will be E, or you can activate by high. So it means chip enable this E and chip select. For example, if we give, the low, it means that it will be chip enable. If we give the high, it will be, it means chip select or power down. Okay. So guys, a computer program is typically referred to as software, right? But however, when a computer program is stored in a ROM, it is called firmware because of the difficulty of making changes. So you should know this kind of differences. Okay. So using a ROM. So here's the last example. I will not show it in the multislim because I don't have this kind of ROM in my multislim, but suppose you have to design a device that will give the decimal counting sequence shown in table. So you need some device. When we switch on this device, it should show on the display some sequence of numbers, for example, 1, 100, 117, 22, then 6, and 100, and etc. Then it should come back to the 1. So how can you implement this one? Of course, you can assemble a logic circuit, or you can maybe use other kind of device, data selector, but there's no any kind of meaning order here. So it's better to use some ROM for this. So actually, so first you convert this decimal readout. You convert to the binary coded decimal. So what next? So actually you write all this information. You order from the manufacturer this kind of ROM that will store this information, and then you can just address your input, give some address, and on the output you will get these numbers. So what you need ROM, you need decoders, 3 decoders, and you need 3 7-segment display. So it will count this number. So you just need to apply some, for example, some counter here. It will just will change the address input step by step, and this output in the 7-segment display will be like this: 1, 1, 117, 22, 6, etc. So when it will achieve the 177, it will come back to 1. Okay, so it is actually truth table for this circuit. So what you need, guys, to understand: read-only memories (ROM) are used for encoders, code converters, lookup tables, microprograms. I don't know, character generators, function generators, microcomputer system firmware, and microcontroller firmware. So actually, inside of this ROM, we already have some data, and when we switched on this ROM, so output will give us this data. Of course, it will depend what kind of address you apply to the inputs, so to the address inputs. So last, what I want to show you guys. Guys, now you are on the level that you can do some more complex. You can assemble some more interesting circuits. You can do it not only on the multislim, but actually can order some integrated circuit and assemble some interesting devices. I think it will be very, useful for you. Okay, so let me show you. I don't know, maybe here, maybe here. Yeah. Okay, first I want to show you some digital clock, guys. So for now you have enough knowledge to make your own digital clock, guys. Actually, you can do your own digital clock. So just imagine that you will order some integrated circuits and you can do your clock. So let me explain in short how it works. Okay, so I see. So I start from the So here is my second, here is my minutes, and here is my hours. So how it works, guys? Let me explain. So of course in the multislim I could not show it, but to do some clock, you know, you need some continuous signal with some frequency. Where can we get this continuous signal with some stable frequency? Do you have any ideas, guys?
In real world or multisim?
Where? So
You're
to
asking in multisim?
not in multislim. I mean just in general.
In real world.
For example, you want to do some clock, but to do clock, you need to count every second, right? Every second. So you need to some stable generators that give you some impulses with stable frequency. So you need to find this generator. Where do you find? If you look around, now you're sitting in your room, look around, give me some.
Alternating current.
Yes, excellent. So you have power line, and in this power line you can take voltage, right? And the voltage of your power line it's 250 volts, and the frequency is 50. Yes, so actually I just modeled this part, but of course here is the frequency is not right. You can just change. So in our case it's 50. Okay, so next, of course, you need to use some transformer because 220 it's too high. So I just divide by transformer. I just reduce this voltage. I don't know, maybe to the level of 5. So actually, we can check it here. I will put my voltmeter. Let's check. Rerun this program. Okay. So what my voltage output? I have any signals? So it's very strange. So actually here I have, you can see after transformer I have about 5 volts, right? But after Schmidt trigger, I don't know, for some reason I don't have any. It's not right. Schmidt trigger. Can you see? It is a lack of inverter. I need to use other one. But anyway, I can just skip this part. So actually, guys, you can take some stable signal with some stable frequency from the power line, but the frequency is 50, right? So how can we reduce this frequency? How can we divide the frequency and get on the output 1 hertz? 1 hertz, it means we have 1 pulse in second. How can we reduce? Do you have any idea? Guys, you did the lab works. Do you remember we use counter? So actually this block I've created myself. So I just double click. So this one. So actually, guys, you can create some circuit and you can just, you know, assemble in some block. So do you remember it is our flip-flops and we connect it like this. It is everyone in the toggle mode and it will be our
Yes.
So by using this counter, actually by connecting properly this NAND gate, you can actually divide your input. Here we have, for example, if my input will be 50 hertz, so on this output I will get 1 hertz. Okay, so let's come back. So then I just represent this counter, just some small blocks. So here my input, and it will be from this transformer after the trigger Schmitz. and just will square up signal. I don't need sinusoidal signal, and the frequency 50. But on the output, I will have frequency 1 Hertz. Then, guys, I apply this frequency 1 Hertz. I apply it here, but here I do not connect because in multi-slim, when I use 1 Hertz, simulation is too small. Because it's not real. It's not in hardware. In hardware, from this you will get it 1 Hertz. So imagine that this generator is this one. So it here give us not 500 kilohertz, but give us 1 Hertz signal. So it actually just connect like this. So I apply to this counter. I apply what to this counter? I apply clock signal with the frequency 1 Hertz. I take it from the power line. So let's consider this counter. I assembled also myself just by using what's this? Guys, it's counter, right? By cascading of these two counter.
Yes.
Yes, by cascading.
Counter in the counter, like up and down.
Yes. So I just cascading these two counter, and this both counter in this combination they will count from 0 up to 59. They will count from the 0 up to 59, and then you can see all the outputs will go to the decoder. So these two decoders just 7-segment decoder. So it will just decode the BCD. They will decode just to the 7-segment code. Okay, but here, if you will pay attention, I added some NOR gate. So I'm using this NOR gate because when it will be count from the 0 to 59, then it will update to 0, 0. I need some other clock that will have frequency less than, not 1 Hertz, that will have frequency less than, so it will be as frequency 1 over 50. So I will take this signal with less frequency, with frequency 1 over 50, and I apply it to this show me to second counter. So this counter will give the input from this the first counter, and it will give the impulse every minute. So this will count. Second counter will count. So also internally they is the same. I have this NAND gate also, so it will count, but now it will count my minutes, and it will count from the yes, from the 0 up to the 59. Yes, then when 60 minutes will be over, through this OR gate it will give signal, and this signal will have the frequency 1 over 60, and it will apply it to this last counter. So this count my hours. So, but when we use hours, we do not need to count from the 0 to 59, right? We need to count up to 12 or up to 23. 23. So I just need to show you. I just want to show you inside how it's look. So I can just choose here. So it is inside the same two counters, but the connection of this NAND gate is a little bit different, because I want to update not after 59. I want to update after 23. For this reason, I connect this not the same as with the previous one. So that's it, guys. It's actually a clock that you can assemble. So you can assemble yourself on multi-slim, but of course on multi-slim it will not work properly because it depends on the processor. So the frequency of this clock, it's not consistent with real frequency. So guys, if you want to improve your score, your grade, so you have about 1 day. You can try, and if you will make this kind of clock, you can get additional, grade. So try. And last, what I want to show you, for example, guys, I want to show you voltmeter. So you know all of these devices except this. It's called operational amplifier. So actually you can find in the chapter 14, you can find how it works. It's not so difficult to understand, but unfortunately we have only 10 weeks in one lecture a week, so I could not cover all of this topic, but it's easy to understand how it works. But it's simple circuit, but it can measure the voltage. So guys, let me show you. So here it is a potentiometer. So I want to measure the voltage. So actually, let me just for a while remove and explain you. So if I connect this one to some wire when I want to measure voltage, so it should be here on this display. So here we call this potentiometer. So actually, if I will, it is a wiper. If I will move wiper, my voltage will be changed. So can you see, guys? Now, maximum I have 8 volts. If I move this wiper in the other direction, it will be almost 0. So you can see 800 nanovolts. So it's almost 0. Sometimes multi-slim give me some headache. Okay. So what's going on? Maybe I can move it. Okay, so can you see maximum I have 8 volts and minimum I have 0. So now I will measure this volt. I will measure voltage by the voltmeter that I made myself. So I'm using for this. So what is counter? I'm using this operational amplifier, and also I'm using this circuitry. So this part is just so this both is just convert from the analog signal to the digital signal. So I will just connect and let measure. So let's put it on the middle. So guys, you can see now it show me 4 volts, right? So let me increase. So it will increase. So maximum I can get 7, not 8. Why? Because I need to adjust this resistor. So you need to calibrate. So maybe I will give 36. It's not enough. Okay, let me increase. I don't know. 40. It's not enough. Okay. 35. No, I need to decrease. Sorry. So let's do it 33. Okay, so can you see? So where I decrease voltage, I need to just refresh it, so it will measure. For example, let's put it on the left position, 0. So guys, it's a voltmeter. You can also assemble this one on the lab. So for this, just read about this operational amplifier. It's not so difficult to understand how it works. But for now, you're capable of assembling some interesting, simple digital system. So it is a digital system. So it's just a digital voltmeter. So it measures the voltage. Okay. Do you have questions about the clock and voltmeter? You can ask. So let me, guys.
No, like we will learn it after learning.
Okay, so
14th
guys,
chapter.
yes, I recommend you when today's last lecture. So I recommend you read this book up to the end. So especially chapter 14 is very useful because it will give some introduction to the analog to digital converter and digital to analog converter. It's very one of the important things, because we always work our real world is analog in nature. So we always need to convert analog signal to the digital signal. Then we can process it. So for it, we need analog to digital converter. Sometimes we need to convert from the digital to analog. Yes, so please don't be lazy, read this chapter 14. It's not so difficult to understand. You already have a lot of knowledge and it will be easy to you understand. Then try to do the simulations. Okay, and next I want to share with you 2 books in electronics, and maybe some of you in the future want to work, not just in developing some software, but maybe you want to program some microcontrollers. If you will program some microcontrollers, maybe you will want to working in the field of embedded system and just develop some smart devices. You need to understand how to interface your digital system with some real world. For example, sensors, I don't know, a lot of things, but especially we always need to connect our digital system to some sensors, and this sensor will, for example, read some physical quantity from the real world. For example, temperature, I don't know, what brightness, pressure, etc. Maybe you want to create some smart home, system. Of course, for it you need some sensors. Then you need to connect this sensor to your microcontrollers, but you cannot connect it directly. You need some analog to digital converters. You need some interfacing. So let me share you these books, and it's up to you. Maybe you'll be interested and you will read this.